Hello everyone. Today's lecture, this is the first part of the condition monitoring system algorithm design. So this is completely a basics, that is introduction about rotating machines, and this is a very important lecture. And in this lecture, you will be going to learn why the machine should be measured. Okay, so let us see, start from the learning objectives. So the learning objectives are reasons for rotating rotary machines measurement. That means what are the reasons why we should measure the rotary machines. Here, what do you mean by rotary machine? A machine having a rotating parts like gear wheels, ball bearings, shaft, etc. And response formula. So how do we measure the rotary machines? By using this formula. So you will be learning what is response formula. Next, before designing the algorithm of a smart condition monitoring system, we will understand what is its architecture. Okay, so first introduction. So rotary machine is measured for two general reasons. So there are two general reasons why we measure the rotary machines. That is namely either to access its technical condition. So whether the machine is working properly, or whether the machine is in good accurate condition, or whether the machine is utilizing the less power. So these all comes under the technical conditions, that is machine diagnostics. And another reason is its model parameters. Suppose you have a very old machine, that is called legacy machine. Okay, and you wanted to develop a condition monitoring system technology for that machine. Then you have to, you don't have any data sheet, or you don't have any previous history of the machine. Then what you do is, in the simulating software, which is a part of MATLAB, you will be learning that Simulink and MATLAB program in the due course of the lectures. Okay, so in the Simulink software, what you do is you will model the machine. That is called a digital twin technology. That means you will model resembles the original, exact, the real machine. So when you are modeling the machine, you will come across so many model parameters. So we have to understand and we have to measure the model parameters. So these are the two reasons why we go for machine measurements. So what is the first reason? First reason is its technical conditions, and second reason its model parameters. So in the first case, a signal is recorded under machine's regular operation. So in the first case, that is when you are going to measure the technical condition, when you are going to estimate the technical condition of a rotary machine, what you do, what is the first task you are going to do is you are going to record a signal under machine's regular operation. That means that normally, that is normal, the machine is operating. In that case, you will record its vibration signals. How you record its vibration signals? By using a sensor known as vibration accelerometer. And next, whatever the signal is recorded, it will be stored. Then after storing the signal, it will be processed. What do you mean by processing? That is, you will be learning in due course of lectures. Just I will brief you what do you mean by processing. Processing is nothing but removing the unwanted information, or removing the unwanted noise from the recorded signal, and then analyzed. What do you mean by analyzed? So analyzed is nothing but extracting the condition indicators. So you will be learning what do you mean by condition indicators, what are the different types of condition indicators in due course of the lectures, in order to gain the knowledge about the current technical state, preferably with respect to some referential data. So suppose if you have some referential data, you have a data sheet, or you have a previous history of the machine, then you will be using that data as a reference data, and you will be comparing whatever the signal is recorded with that reference data. Suppose if you don't have the reference data, or if you don't have the previous history of the machine, then you will go to the second case, that is you will model the machine in a Simulink software. So in the future lectures, I will take an example of gear transmission system. That is one system in a rotary machine, which I will explain you how to model that system in a Simulink software, and we will be developing complete condition monitoring system algorithm, all the steps by using that example. Okay, now we will see in the second case, the object of the machine is measured to learn about its internal properties, namely natural frequency, damping parameters, and model shapes. So these are the three parameters which are the internal inherent or internal, both are same. So properties, so namely natural frequencies, damping parameters, and model shapes. So you can see, so this is the test bench as an example. So you can see here, this is the motor and this is the gear transmission system, which you are going to learn about this system in future lectures. And here, see here, this is a shaft. So the shaft is connected with another motor here, and these are the whatever the cables you are seeing here, these are nothing but accelerometers. See, you can see these are accelerometers mounted on the casing of the gear transmission system. This is a casing. What do you mean by casing? Casing is a stationary object which protects the internal gear wheels, shafts, etc. So you have input shafts and you have the output shafts. So this is a very good model, especially for the for understanding the condition monitoring system design algorithm. Although many model analysis techniques have been developed over the years, the most common technique requires a controlled, measured force excitation of an object collected in parallel with multi-point systems response measurement. So, although many model analysis techniques have been developed, so lot of research is going on in and around the world, so on this condition monitoring system algorithm, and so many model techniques or model analysis techniques have been developed over the years, but the most common technique requires a controlled measured force excitation of an object collected in parallel with multi-point systems response measurement. That means, if you see here, if you see, we are collecting with a multi points. That means, see here, we have connected one accelerometer, here we have connected one accelerometer, like that. So different from the different accelerometers, we are collecting the data. Okay, this is called a multi-point system response. Both of these measurement approaches are commonly represented in the frequency domain by equation shown in the next slide. So both of these measurements, what are the two measurements? Just now we have shown you, that is its technical condition. Second one is its model parameters. So both of the measurements, whatever we take, we will be represented that we will in the frequency domain. That means, first the signal is recorded in the time domain, then we convert that signal into the frequency domain. Suppose if you are modeling the machine in a Simulink software, then it is you the complete data or the complete signal will be under your control. So you can easily convert that complete time domain signal into a frequency domain. So there is some standard equation for that you will be seeing now. So this is the equation, that is, this is called a response equation. So response is equal to force into FRF, that is frequency response function. So let us understand this formula in detail. So in practical measurement of a rotary machine, the response is the actual data collected by the data acquisition system. So what is the response in practical measurement? Response is nothing but the data which is collected by the data acquisition system. So just you will see now, you can see here, let us take this accelerometer. This accelerometer is connected to the casing of the gear transmission system. So now the data will be collected from this accelerometer, and this is an analog cable. You can see the black cables here. So this is an analog cable. So from this cable the data travels and reaches the data acquisition system. Okay, so this is called a response. Now, coming to, let us understand the its complete architecture. So, before analyzing this equation, so in order to understand this equation, we are showing the practical, that is a real architecture of a SCMS, that is Smart Condition Monitoring System. You can see here. First, I have taken a CNC machine as a machine, rotary machine. Okay, CNC means computer numerical controller. These machines will be useful for manufacturing the tools and dies. And this is our condition monitoring system algorithm present in this box. So this is called an edge box, and this box is directly connected to the machine, so through wires. So this is called a physical connection, like you have seen now. In that machine, the accelerometer is physically connected to the machine. Now, from the edge box, so in this the condition monitoring system algorithm will be there. So this algorithm will be running, and whatever the data collected from the machine, you will be doing processing, you will be doing analysis. Analysis is nothing but extracting the condition indicators. Then you will develop a artificial intelligence model. So for gate transmission system, we are using SVM, that is supported vector machines. You will be learning that in the future lectures. So we will, whatever the condition indicators have been extracted, we will train the model with that input, that is a feature table. Okay, feature table consisting of all the features of that particular signal. Okay, and we will be understanding, we will be seeing like how we have identified the faults. That means what are the predictors and what are the responses, and how we have predicted the fault, and with that fault how we have identified which part of the gate transmission system got a fault, whether the gear wheels or the ball bearings or the shaft, etc. And whatever that result will be stored in a server called MySQL server. This is a completely IT related domain, and this we will take one system, physical system, normal computer, and we will convert that into a server, and this server is connected to this edge box via internet. This is called IoT. Okay, and from the SQL server, whatever the result, if you want to see, that is the end user, so you can access the server through a internet. So this is the simple architecture of a condition monitoring system algorithm or condition monitoring system design. Now, let us see what are the main parts present in the edge box. So one is the data acquisition system module, or we can call DAQ module, and this module belongs to a company called National Instruments. We are going to use this module, so that is the reason. There are other modules also. There are so many other vendors present in the market. You can choose as you like, but my suggestion is NI modules are high accurate, so we are using this one, and also these are easily supporting to the MATLAB software. Next one, you can see here, this is a Intel mini processor, and this processor is nothing but used as a mini computer, where you will be storing your algorithm. Your condition monitoring system algorithm will be running in this processor. And here you can see this is a Wi-Fi router, normal Wi-Fi router, especially used for the internet purpose, because we are using the IoT also, because our SQL server and end users will be connected to the edge box through IoT. Now, so this is the centralized MySQL server. Okay, so now in the laboratory scenario, with negligible noise floor level and responsible adjusted dynamic range of the physical channel, the left side of the equation is directly known. However, the right hand side of this equation, so which equation? That response equation. So response is equal to force into frequency response function. So however, the right side of this equation takes different meaning for the two measurement approaches, which are already I have shown you. So when the machine diagnosis is undertaken, typically only the system's response is measured as illustrated in figure 1. So already I have shown you. So in this case it is hard to tell the uh, contribution of the force versus the contribution of the frequency response function to the resultant spectral amplitudes of the measured signal. In case of a simple model analysis, the force is measured during the excitation separately for the instance at machine standstill, which allows relatively easy calculations of the object's FRF. This concept is schematically illustrated in figure 2. So you can see this is the response is equal to this is the force into this is FRF. So formula, so response is nothing but whatever the data we collected from the accelerometer, we are getting the uh, uh, plots, that is the raw data, and this is the force, whatever the force, like for example this response will be getting from this accelerometer, and force means we are from which machine we are collecting the data. Let us take a force, that is a motor, and multiplication is end, and this is the gearbox, that is the frequency response function, that is a gate transmission system. Okay, so you can see here, this is the path 1, that is vibration based condition monitoring analysis, and this is the model analysis. That is, what is this model analysis? This response with combination of force, that is a pulses, is equal to FRF. In this case, both signals are used to calculate the FRF. Note that the simplified scheme illustrated in figure 2 refers to signal amplitude. However, the just like any FFT based processing enables analysis of both amplitude versus frequency and phase versus frequency. So in model analysis, the phase is used for instance to verify resonant frequencies and to plot the model shapes. So in model analysis, whatever the model analysis I have shown you, this is the model analysis. So see, this is the model analysis. So in this model analysis, this is the phase values of FRF, whatever we are measuring here. In rotary machinery diagnostics, the phase is typically used for signal resampling, and which requires additional measurement of phase data. So normally in the rotating machines, the phase analysis will be done, especially for signal resampling. Resampling means in exact samples of the signal. One might think that in order to separate the force from the FRF, it is sufficient to measure and subtract the FRF from the operational data, but this is not possible because the FRF of a stopped machine differs from that of a working machine due to additional driving force and load transfers. So you can see here, you can see this figure, you can see let us for example take a machine is a stationary machine, that means it is not under operating condition. Now if you wanted to subtract the FRF from this two, that is a freak response and force, it is not possible because it is possible, but once the machine starts working, then that FRF is different from the stationary FRF. Because why? Because additional forces will be developed. So as a consequence, a typical vibration analysis within machine diagnostics assumes a simplified scenario where that the FRF of the object is constant, and therefore the analysis is oriented towards detection, monitoring, and analysis of changes in excitation force coming from faulty motors, shafts, gearbox, blades, belts, and bearings, etc. The major number of vibration-based techniques thus assumes that any fault in a mechanical element generally generates additional, which are the counterbalanced by newly generated vibrations, generally called signal of interest. And what is a signal of interest? See, the major number of vibration based techniques thus assumes that any fault in a mechanical element. What are the mechanical elements? You can see motor, shafts, gearbox, blades, belts, and bearings, etc. So these are all called as a mechanical elements. So any fault that is generated in that mechanical element additional, which are counterbalanced by newly generated vibrations. So its own vibrations also will be generated, which are called signal of interest or SOI. And that the major goal of such measurement is to either detect its presence if absent earlier, illustrates the relative growth if reference data is available, or to define the rate of their growth if prognostics is desired. So that means why we are going to measure the signal of interest. The major goal of such measurement is to either detect the fault if the fault is not present earlier, okay, uh, by using the referential data or the previous history of the machine. In some cases of rotary machines, this analysis is additionally problematic because some forces are periodic, like gearbox mesh excitation from electrical motor, while some load model parameters are time variant, like gearbox meshing stiffness functions. Note 2 signal represents illustrated in figure 1. When the signal is analyzed in time domain, the response is so-called convolution. So if you analyze the signal in time domain, that is called convolution of the force, and it transfers and the transfer function, which while in frequency domain it is simple multiplication of the force and the FRF, that is TF represented in the frequency domain. Referring to figure 1, you already have seen convolution is a signal processing filtering function with the two functions as input arguments, forces and TF, that is frequency domain. More precisely, the TF is a pulse response of the system which acts as a filter. Practically, convolution could be explained as a set of few mathematical operations on a signal, namely signal reversing, signal shifting, multiplication, and integration. So these are all some of the mathematical operations which can be explained practically. Okay, what is a convolution? Convolution means it is nothing but a few mathematical operations on a signal, namely signal reversing, signal shifting, multiplication, and integration. The wide range of resulting possible data processing paths within the vibration analysis results in a variety of sensors, equipment, measuring technology, signal processing methods. Signal is analyzed by using various technologies and condition monitoring system architecture. So now in this lecture, what you have learned is a professional machine measurement should not rely on arbitrary equipment. So that means when you want to measure the machine, the equipment must be industry standard, not simply like any arbitrary normal, like best example I can say you is Arduino sensors, So those are all belongs to the educational side. So you cannot rely on that type of equipment which happen to be available at the present time, but it is an interdisciplinary science. See, this technology is an interdisciplinary science. That means it involves mathematics, it involves artificial intelligence, it involves programming, it involves mechanical concepts, everything. So it is an interdisciplinary science which should take the advantage of various measurement and data processing techniques. So thank you so much for watching this presentation.